US Physics Olympiad year 2018, USAPHO, problem B3. Radiation pressure from the Sun is responsible for cleaning out the inner solar system of small particles. Question A. The force of radiation on a spherical particle of radius small r is given by formula F equal PQ P r square, where P is the radiation pressure and Q is a dimensionless quality factor that depends on the relative size of the particle r and the wavelength of light lambda. Throughout this problem, assume that the Sun emits a single wavelength lambda maximum. Unless told otherwise, leave your answer in terms of symbolic variables. I. Given that the total power radiated from the Sun is given by Ls, find an expression for the radiation pressure at distance r from the Sun. II. Assuming that the particle has a density ρ, derive an expression for the ratio F radiation over F gravity in terms of Ls, mass of Sun ms, ρ, particle radius r, and the quality factor Q. III. The quality factor is given by one of the following. Consider the three possible particle sizes, which is most likely to be blown away by the solar radiation pressure. Solution for part A. Question I. Given that the total power radiated from the Sun is given by Ls, find an expression for the radiation pressure at distance r from the Sun. Solution. We can use here expression for a formula which connect impulse and energy of one photon. Impulse equal energy over speed of light. The power will be energy over time. So when we summarize all impulses for photons, we will get formula that the total impulse equal total energy over speed of light. And we can assume this formula as this. And the change of this impulse over area, that will be pressure. So we have pressure equal total intensity over speed of light, or power over 4 pi r square c. So that was answer for question I. But alternatively, this relation can be derived using classical electromagnetism, though this was not required. For a plane wave, the momentum density of the electromagnetic field is by this formula, while the energy density is this one, where S is a Poynting vector, like this. So we have pressure equal intensity over speed of light, because c square equal 1 over epsilon 0 mu 0. That's answer for question I. Question II. Assuming that the particle has a density ρ, derive an expression for the ratio F radiation over F gravity in terms of Ls, mass of Sun ms, ρ, particle radius r, and the quality factor Q. Solution. Force of gravity equal this expression. Force of radiation equal this expression. So we have relation. And finally, ratio F radiation over F gravity equal this expression. That was answer for question 2I. Question III. The quality factor is given by one of the following. Considering the three possible particle sizes, which is most likely to be blown away by the solar radiation pressure. Solution. In order to be blown away, the ratio should be greater than 1. Since it is independent of distance from the Sun, if it is blown away, it will be blown away at any distance. For r much greater than lambda, the ratio is proportional to 1 over r, so smaller particles are more likely to be blown away. For r much less than lambda, the ratio is proportional to r, so large particles are more likely to be blown away. Thus, particles of size near lambda are most likely to be blown away, and even then, only if the density is small enough. That was answer for problem B, part A. Part B. The Poynting-Robertson effect acts as another mechanism for cleaning out the solar system. I. Assume that a particle is in a circular orbit around the Sun. Find the speed of the particle v in terms of ms, distance from Sun r, and any other fundamental constants. I. Because the particle is moving, the radiation force is not directed directly away from the Sun. Find the torque tau on the particle because of radiation pressure. You may assume that v much less than speed of light c. I. Since tau equal dl over dt, the angular momentum L of the particle changes with time. As such, develop a differential equation to find dr over dt, the rate of change of the radial location of the particle. You may assume the orbit is always quasi-circular. I4. Develop an expression for the time required to remove particle size r about 1 cm and density 1000 kg per meter cubic, originally in circular orbit at a distance r equal r Earth, and as numbers below to simplify your expression. Some useful constants include. Solution for questions in part B. Assume that a particle is in a circular orbit around the Sun. Find the speed of the particle v in terms of ms, distance from Sun r, and any other fundamental constants. Solution. Using the circular motion equation, we have gravitational force is responsible for centripetal acceleration. So we have this formula, and from here we have speed equal square root from gm over r. That's answer for problem 1 in part B. Question 2 from part B. Because the particle is moving, the radiation force is not directed directly away from the Sun. Find the torque tau on the particle because of radiation pressure. You may assume that v much less than speed of light c. Solution. We work in the reference frame of the particle. In this frame, the radiation hits the particle at angle theta equal v over c from the radial direction. The particle then re-emits the radiation isotropically, contributing no additional radiation pressure. We ignore relativistic effects because they occur at second order in V over C, while the effect we care about is first order. The tangential component of the force is this one. So the torque will be this one. This is the answer for question 2 in part B. Question 3. Since tau equal delta L over delta T, the angular momentum L of the particle changes with the time. As such, develop a differential equation to find dr over dt, the rate of change of the radial location of the particle. You may assume the orbit is always quasi-circular. Solution. By the way, we had a negative sign for torque because this tends to decrease the angular momentum. Solution for question 3. Solution. The angular momentum is this one. Now we can take a first derivative by time from both parts, and we have torque equal dl over dt, or what we did before. It's this one. And with simplifies to this equation, we have this answer for question 3 part B. This is our differential equation to find dr over dt. So that's answer for question 3 part B. Question 4 from part B. Develop an expression for the time required to remove particle of size r approximately equal 1 centimeter and density about 1000 kg per cubic meter, originally in circular orbits at a distance r equal radius of distance of Earth from Sun, and as the numbers below. Simplify your expression. Some useful constants include these expressions, this meaning. Solution. We have a differential equation like this. So if we split expression, and after integrating we have time equal this expression. So if we know what distance we have to remove particle from the Sun, we can put it instead of r1 and count what is total time. That's a solution for question 4. And that was a solution for total problem B3.